Rockets have been and are our only way to get to space, and that's probably not gonna change for a while. So why don't we talk in this first episode about how rockets work?
That's 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
This episode is going to be quite different to the others, because instead of talking about great missions or history, I'm going to focus on how rockets work, to help you understand the space missions that we're going to talk about in the next episodes. Let's start with a brief overview of the laws of motion, which are key to understanding the rest of the video. These three laws were published in 1687 by Sir Isaac Newton. The first of them is the law of inertia, which explains that if no force is acting upon a body, that body won't change its movement, which means that it won't speed up, slow down, or turn. On Earth, vehicles have to accelerate constantly because friction with the air and the ground is continuously slowing them down, and that happens to rockets as well until they leave Earth's atmosphere. The second law gives us the equation that defines the concept of force. Force equals mass times acceleration. It basically explains that, obviously, the more massive an object is and the faster we want it to accelerate, the bigger the force we have to apply to it. 1 Newton, which in order to Isaac is the unit that measures force, is the force that we have to apply to a body of 1 kilogram so that it accelerates 1 meter per second. 1 meter per second equals 3.6 kilometers an hour or 2.24 miles per hour. You should get used to hearing this unit because it's the most commonly used in science and the one we're going to use in this series. The third and last Newton law tells us that for every action there is a reaction in the opposite direction and with the same force.
So I've got on my sister's skateboard in order to have a surface with less friction, and we're going to do a couple of experiments. So in the first one I'm going to throw this very light object, and we'll see that there's no appreciable effect. Still here. So I'm going to try something a bit more drastic. So I'm going to throw this just a little bit so that you can see that there's not much effect. And that's all. Let's try harder. Okay, there was more effect this time.
In space, there's nothing to throw backwards to push yourself, so the only thing you can do is take it with you. For example, in order for a car to move forward, what wheels do is push the ground backwards, although the effects of that are transmitted to the whole Earth and therefore are imperceptible. Another example. What a plane does to move forward isn't moving the ground backwards because it's obviously not touching it. Instead, it takes the air that gets into its engines and accelerates it backwards to push itself. What a rocket engine does is push matter to the opposite direction in which it wants to move and tries to push it as fast as possible because the same mass of propellant, if pushed faster, equals more force that will push the rocket. The engines you see on Earth just burn fuel. But we shouldn't forget that in order to have combustion, oxygen is needed. That's no issue for cars or planes since oxygen is abundant inside the Earth's atmosphere. But there's no oxygen in space, so rockets have to take that with them as well. Two substances react in a rocket engine. One acts as fuel and the other as oxidizer. There are many types of rocket fuel, but the oxidizer is almost always oxygen. The purpose of the chemical reaction is for those elements to transform into others releasing energy, which then propels the resulting substances of the reaction outside of the engine as fast as possible, so that the rocket moves. I said as fast as possible because for the same mass of propellant, the more you speed it up, the more thrust you'll get. The two most common rocket fuels are hydrocarbons, which include methane and kerosene, and hydrogen. Here you can see the reaction of hydrogen and oxygen, which produces water and energy. The energy then propels the water. The same happens with methane, which is the simplest hydrocarbon, and oxygen. The most commonly used hydrocarbon is kerosene, which is a molecule a lot more complex than methane. And that's how liquid fuel engines work, but there's another type, the solid fuel engines. In this case, in the fuel tank, the fuel and oxidizer are mixed in a solid form with a hole in the middle. When the engine ignites, a violent reaction like the previously mentioned ones begins, and everything goes down through the hole until it comes out. The bad part is that you can't stop a solid rocket engine because the fuel and oxidizer are combined. So once it ignites, you have to deal with the consequences, good or bad, until it runs out of fuel. Now that we know the basics of how rocket engines work, let's see what they do to get to orbit. The first thing I want to make clear is that their objective isn't to go upwards. If they did that, they will fall back to Earth and crash. Their main goal is to go sideways to orbit the Earth. That means turn around the Earth in a stable way. The reason why they need to go upwards at first is that they need to leave Earth's atmosphere. Otherwise, it will slow them down until they fell back to the ground. The atmosphere will also burn them if they try to go very fast inside of it. So, in summary, what they need to do is make the most efficient trajectory, that means the one that uses the least amount of fuel, to get out of Earth's atmosphere and reach enough speed to get to orbit. In order for it to be more visual, I built a rocket cheated so that it never runs out of fuel. Its goal is to help me explain how a rocket gets to orbit without worrying about fuel running out. As you can see, the rocket's lifting off, and obviously real rockets are bigger than that. That's just the trick one I told you about. And on the right side you can see the map of Kerbin, which is the Earth analog in this game. And as you can see, it's indicating you the apoapsis, the Kerbin apoapsis. So what is an apoapsis? Okay, the apoapsis is if the rocket suddenly stopped burning fuel, if the engine stopped, the rocket would continue with its trajectory until it reached the highest point, and the highest point is the apoapsis, and then it would fall back to Earth, or Kerbin. So, what the rocket's trying to do is rise the apoapsis until it's outside of the atmosphere, and then continue with the maneuver so that it has the stable trajectory that we'll see later on. So, the rocket, well, we now have some technical difficulties. I hope it's not a problem. That's it. So, the rocket is on a curved trajectory, which means it's not going straight up, because the most efficient way to get to orbit isn't just to go straight up, as I told you before, because it would then fall back to Kerbin or Earth. So, on Earth, you are in space if you are higher than 100 kilometers. That's just an official way, an official measurement. But in this game, you are in space if you are above 70 kilometers. And above 70 kilometers, there's absolutely no air. But in real life, the atmosphere gradually disappears. So, to get a stable orbit on Earth, you should be higher than 200 kilometers. But in the game, I've set up a 120 kilometer orbit. And as you can see, the rocket has stopped burning fuel because it has now raised the apoapsis to 120 kilometers. So it'll now wait and it will warp a bit, so the time will go faster for a while. That's just the game. That's not what happens really, obviously. So now it's about to burn. Now it has stopped warping and it's now in the apoapsis, in the highest point of the trajectory. So it will now burn till it is in the orange trajectory, which is the one we want, the orbit. So as you can see, the blue trajectory, which is the one that the rocket is currently in, is wider over time. So now we have a periapsis, which is if the apoapsis is the highest point of the trajectory, the periapsis is the lowest point of the trajectory. So now we have an apoapsis and a periapsis, both of them above the atmosphere. So that means that we are in a stable orbit. Very well. Now that it's in orbit, I'm going to explain how orbits work. They can be a bit counterintuitive at first. So, I'm burning in the same direction in which I'm going. That means I'm speeding up in this part of the orbit. And by speeding up in this part of the orbit, what I'm doing is increasing the distance of the other side of the trajectory to the planet. So, now, as time passes, now I'm further to the planet than in the other side. Now I'm going to do that in the other side of the orbit. I'm going to circularize the orbit, because I'm going to burn here now in the same direction in which I'm going, and that what it's going to do is the same thing but in the other side, increasing the distance to the planet. So it's now more or less a circular orbit. That means that it doesn't really matter what the periapsis and apophysis are. And now I'm going to do that, but in the other direction I'm going to decrease my velocity. So what that has is obviously the opposite effect. And this is the end of the first episode of the story of space exploration. Congratulations! Now that you know the basics of rocket science and how rockets work, you're ready for episode 2, the beginning of the space race, in which we'll review since the construction of the first liquid-fueled rocket to the launch of the first satellite, going through World War II. Very soon on Planet Genesis.